Good morning, everyone. So last time we were talking about naming cations, or starting to get into the category of naming ionic compounds, where we want to name the compounds that are comprised of ions. Often we'll see that these are contain a metal cation and some sort of non-metal ion. Ammonium is a weird one where we have a molecular cation. Oh, I removed my iPad. Got to reconnect here. Here we go. So ammonium was one of the cations we saw last time. It's a molecular cation where we have 4 hydrogens attached to a nitrogen. Later we get into structure. Later we get into sketching these like Lewis structures so we can get a picture of what something like NH4 looks like. So NH4 plus looks something like this. We'll see later the positive charge is mostly residing on that central nitrogen atom. In terms of sketching the structure, this is like a chapter 8 topic, so we'll come back to that later. But we see this cation here, and then we see Cl-, that's the usual ion of chlorine. So Cl- is chloride. We haven't really gotten to systematically naming the anions yet, but you'll probably pick up that these simple ions where we just have one element with a charge just takes the IDE suffix. So then oxide would be the simple ion of oxygen. And then we kind of look at oxygen's placement on the periodic table and see that it needs to pick up 2 electrons to go to a stable count of electrons. So O2- would be oxide. Chlorine, being in the halogen group, goes to Cl-. So we have F- fluoride, but we'll pick up some of those anion nomenclature systems in a few moments. But to name NH4Cl, we're just kind of picking up the name of the cation as ammonium, and then chloride. For the most part, we're doing nomenclature questions on a test from like a multiple choice basis. So a lot of times you don't have to spell these things, so we're not really trying to get a whole lot of nuance into the spelling of the words. We're usually just trying to get can you get the element? Can you get the cation? Can you get, in the case of transition metals, can we get the right charge? So when we see Hg2Cl2, we might not know where exactly to begin here, but where I would start is with the chlorines. That each of the chlorines has a minus charge, because they're just the simple chloride ions. So the name of this compound is going to be something chloride. And so we have 2 chlorides for an overall -2 charge to the 2 Cl-. So that means that the entire group of 2 mercuries has to have a +2 charge. And so this is that weird case, if you remember at the end of class last time, we were picking up Hg2, 2+, was what we were calling mercury 1. So this compound here is one that we just have to know is mercury 1 chloride. Now we'll pick, the reason why we're even mentioning this compound, it's not the most common of compounds. We'll see an example of mercury salts in chapter 4. So I like us to kind of pick up that Hg2Cl2 is this, what we might think of as a mercury 1 chloride. Now, what goes on with mercury is it forms some type of attachment between the 2 mercuries where it forms kind of like a metallic, like a molecular type bond, kind of a similar type bond that you might expect between the nitrogen and hydrogen in ammonia. So we get this attachment of the 2 mercuries, and then we get a positive charge on either end, hence that's the Hg2 with the 2+ overall charge. So it's kind of like each mercury has a +1 charge, but they're attached together. And one thing that I sometimes do is, when we're naming this as mercury 1, is I kind of like think of this in quotes, right? Because it's like on average an Hg+. So on average, it averages out to a mercury with a +1 charge. Mercury 1 by our usual nomenclature system would be Hg+. We would think that would be what we think is mercury 1. But we have to know when we say mercury 1, we really mean this. That we really mean the attachment of 2 mercuries with a + charge each for an overall 2+ charge. So not the most common example. You probably won't see too many examples of this. There's a couple examples on my daily quizzes just to make sure we get the difference down between what a mercury 1 compound would look like or be named. And then we also have the existence of mercury 2 plus as a cation as just the ordinary 2+ charge that you might expect. So most transition metals exist as just like the metal with its charge, single atom. And so here we'd have mercury with the single atom, 2+ charge, 2 chloride ions for a -2. We have to have the positive and the negative charges balance each other out here. That's how we can work out the charge has to be +2 of mercury, is by kind of noticing the minus chlorides, 2 of them -2, +2 for the mercury. This compound here would be mercury 2 chloride. Then FeCl2. Again, we're picking up 2 chlorides, -2. That's how we deduce the charge on, I think I said mercury again, but this is iron, so Fe's iron. So we pick up the -2 from the 2 chloride ions, +2 for the charge on iron in this compound. So this is how we're going to pick up that this is an iron 2 chloride. So the 2 here means the 2 plus charge. So the 2 plus charge is what goes as the iron 2, not necessarily the 2 chlorides. So it's not iron 2 because there's 2 chlorides, it's iron 2 because of the charge of the chlorides that they bring to this being FeCl2, iron 2 plus. Let's contrast this a minute with the oxide of iron, FeO. This is, might drive home the message of this still being an iron 2. So this is an ordinary oxide ion, 2 minus charge for the oxygen, so a 2 plus charge for the iron. So this, of course, would be iron 2 oxide. Just making sure we see the 2 didn't have anything to do necessarily with the 2 chlorides. It just had to do with the charge that the chlorides have that balance out to the charge of the iron having a 2 plus charge. FeCl3, 3 chlorides, -3 for the collection of the 3, and then a 3 plus charge. So this is iron 3 chloride. And now let's think a minute about what this might look like. If we had an iron with a 3 plus charge, this would just mean that we have a chloride ion, and a chloride ion. So the chlorides would be separate, and then each attached to the charge or attracted to this positive charge. And so just kind of picturing that we don't have like chloride, fluorine or whatever. The 3 chlorines aren't attached together. We would have separate chloride ions being attracted towards that 3 plus charge. And then if you're picturing a solid of iron chloride, then you'd probably be thinking that there's probably another iron over here, chlorides hanging off of it as well, where we have this extended structure of plus minuses alternating throughout the structure. So now what about if we give you a name? Can you give us the formula? Most of the nomenclature is going to be, if I give you a formula, can you give me the name? If I give you the name, can you give me the formula? It's not going to be, does this salt exist? Does that exist? It's not predicting the existence of these compounds. It's not trying to say why we're naming, like why do we get iron 2 and iron 3 and not a lot of iron 1 compounds? We're not trying to get into those types of questions yet. We're just trying to get into, if I give you a formula, can you give the name? If I give you a name, can you give me the formula? We mostly keep our examples to things that tend to exist. We don't try to name a lot of things that are hypothetical, so we want to name most of the compounds that exist. So you can start to get the hang of things that we're naming a lot are probably more predominant in nature or in examples or things that maybe you can buy as chemicals in those particular forms. So aluminum oxide, how do we name this? Or how do we write the formula? Well, look at aluminum on the periodic table. It's a 3 plus, and it's ionic compound. So the only ion we get of aluminum would be a 3 plus ion. The ion of oxide would be, or the ion of oxygen for oxide would be an O2 minus. And then we're just balancing out the charges. So here we might do one of these things where we do an Al2O3, and we could double check. We're just making sure that we get a 6 minus and a 6 plus balancing out for those charges. Okay, so we just want the smallest multiples that balance out the charges here to be overall neutral. So we want overall neutral compound, 6 plus minus 6 equals 0. So Al2O3 would be the formula. I just want to make sure that the charges aren't really part of the formula. They're part of the balancing. They're helpful to think about. Sometimes I'll also write formulas and maybe just circle out the actual formula to keep it separate from the symbols we're just writing to help us come up with the formula. And then lastly, 2 examples. So transition metals. The metals, obviously, from scandium across to zinc, those are our transition metals. Those are the ones that we're putting a Roman numeral symbol. So we're using the Roman numeral symbol for things like iron, for things like copper, for things like chromium, etc. Zinc and silver were the two weird ones, where zinc is always a 2+ according to our nomenclature, so we just have to know zinc ion is zinc 2+, so this would be ZnCl2. And then silver 1 is the only common ion of silver, so we just tend to know silver is Ag+, so Ag plus Cl-, so that would be, let me write it over here, this would just be silver chloride. So silver and zinc are the two transition metals that we're not going to be worried about calling it zinc 2 chloride. So we'll just call zinc chloride zinc 2+, so, and we'll just have to know that zinc 2+. And then silver chloride, we won't generally write the silver 1, even though it's a transition metal, because it's the only common ion of silver. Not quite sure why the book wants us to know those two, because they're not exactly the most common of examples. But that's what the book does, and then that's what we take on exams, so that if we put AgCl, we just want it to be silver chloride. Or if we call, like usually by name is where you get caught up. If we call something like zinc carbonate, we start to learn carbonate later, you just have to know that zinc 2+, then whatever the charge of carbonate is. It's crazy. Okay. That aside. Okay, just a few other things. This was like in the notes, kind of where we were going to pick up from the previous slide, was just a few other simple examples of just sodium chloride. Now, when you come back to the alkali metals, the first group, the alkaline metals, the second group of elements, here we're just using their placement on the periodic table for like magnesium 2+ as being the only possible cation of magnesium in a stable compound. So this would be magnesium chloride. So for the elements that commonly form just one stable cation, we don't need to use like a Roman numeral system. So sodium is always a sodium plus, magnesium is always a 2+. And then chloride, we don't have to write dichloride if you remember, because we're just balancing out the charge of what we know to be a minus ion and then what we know to be a 2+ cation for MgCl2. So magnesium chloride for MgCl2, 2+ and 2- for calcium oxide. -2 again, plus for alkali metal. So sodium oxide for Na2O. And then we haven't really seen nitride, but nitrogen, the common ion of nitrogen being 1 from oxygen, that the nitride ion would have to be that simple 3- ion. So 3- to get to that noble gas count. So nitrogen has 5, well, let's not use that word. So if we look at nitrogen and just say for a nitrogen atom, how many electrons does nitrogen have? If you remember the proton-electron counts. So from the proton count, we'd be looking at the atomic number. The atomic number is 7, so we have 7 protons in the nucleus of a nitrogen atom. A neutral nitrogen would have 7 electrons, equal number. And then the count for N3- would pick up 3 extra electrons to go to 10. So we have 10 electrons, same count as neon, so we're picking up that noble gas count of electrons with the N3- ion. Magnesium being a 2+, brings us to another case where we can sort of just lasso out the charges for 3 magnesiums, 2 nitride ions, 6-, 6+ for a quick check, to have a neutral compound. So magnesium nitride, we can write the formula as Mg3N2. So our main driving thought for a compound here is charge neutral. Think about the charges of the ions and then balance out the count of each of the ions to give the compound a neutral charge. Okay, so let's get into the anion side. Let's first talk a little bit about polyatomic ions. We mentioned this already with things like mercury 2+, and ammonium, NH4 with a positive charge. So these are collections of atoms together that we would call like a molecular or polyatomic ion, where we have multiple atoms connected together sharing the charge. Now, these polyatomic ions have some kind of structure, which we'll get into later. Like one of the Lewis structures you might write for SO4 2- kind of looks like this, where we'll see the balance of charge later. But chapter 8, we'll be trying to learn how to sketch these types of Lewis structures, but you can kind of see that there's these covalent bonds, the sharing of electrons between the sulfur and oxygen atoms, and something like sulfate. But the key for this chapter is just going to be trying to recognize that we have sulfur, 4 oxygens, 2- charge, that collection of atoms is what we mean by sulfate ion. So that's just something we're gonna have to come to know. There's not much of a rhyme or reason that we're showing right now. Like we're not trying to say, well, this is, sulfate doesn't exist with a minus charge or a 3- charge, it only exists with this 2- charge. The 8 ending, the ATE ending for our anions usually signifies for the given element of sulfur that this would be the most common or most found type of anion in nature. So we call these things often oxyanions. So the oxyanion of an element that's most prevalent in nature often takes that ATE ending. So the most common example of sulfur is probably going to be this sulfate example. Now we're going to see that there's a connection to other ions that tend to be common for these types of oxyanions. Let's first just remember for our simple atomic ions of nonmetal atoms, just take the IDE suffix. This is what we were already talking earlier for our simple atomic ions like chloride, oxide, nitride. Just looking at periodic table placement gives us the name of the element, followed by IDE. The only thing that gets a little tricky sometimes is where do you cut off the element name? Like for oxygen, why not oxygenide or oxygide, or why oxide? And it just is oxide. We're not usually trying to test you on those nuanced details. So sometimes when you first get to nomenclature, you get a little bit confused of why is it nitride and not nitrogenide. Phosphate's weird because you can have like phosphonates, but you can also have phosphates. So there's the way you cut element names off isn't really what we're exactly testing you on. It's just kind of picking up that if you see the IDE ending, then you know that should just be a charge on one single atom. And so like Br- would just be bromide. So we're just looking for that IDE ending. Hydrogen with the minus charge, this would be hydride. So picking up its nearest noble gas kind of electrons, so this gives hydrogen 2 electrons in its ion form here, matching helium's count. Okay, so then getting into polyatomic ions, we tend to see that we have the representative, the ATEs kind of in the middle here. The first one is carbonate with the ATE ending. So for carbonate, CO3 with a 2- charge is its most stable count of oxygens, and it's charge that we find in nature. So we have to memorize the 3 for the oxygen for carbon, and the 2- charge is what we call carbonate. Now carbonite is where we lose an oxygen off the formula. The charge stays the same as 2-, so we just go from a 3 to a 2 on the oxygen count, and this goes to carbonite. So systematically, we just go 8 to ite when we lose that O atom off the formula. So we see this for the first couple examples here. So we have nitrate being 3 oxygens, but with a minus charge. Again, we're not trying to talk about why it's a minus and not a 2-. We're just saying NO3- is an anion you're going to see in a lot of examples. We just have to know that that's nitrate. If you lose an O off the formula, I'm sure you can all imagine the name, it's just nitrite. So nomenclature starts to take a bit of a point where we can either try to learn that systematic rule. If we learn the 8s, then we learn all the ites by definition, or we can just memorize everything. But I think we just memorize the simple system. If we know that 4 with a 3- is that common ion of phosphorus, that this would be phosphate. So the ATE ending, and then of course if you lose the I, would just be phosphite. So PO3, 3-, phosphite. So sulfate, sulfite are next. Anybody remember that silly like phrase to remember the count of oxygens in a charge? Anybody ever learn this like Nick the camel or something? Does anybody remember learning? Some student once said that there's this thing that like Nick the camel, for Nick, I can't remember the rest of the phrase. If somebody remembers it, that like for nitrate, it was like the consonants were the number of O's and the vowels was the charge. And I heard this one day, and I'm like, wait, it's just easier to memorize, I think, that NO3 minus is nitrate. I don't know how that is any easier. If anybody remembers that, nobody ever heard that before? All right. Well, if you Google Nick the Camel, something, I don't know. But I think it's just easier just to memorize those names. So that's kind of the first 4 examples for carbon, nitrogen, phosphor, sulfur for their most common oxyanion. And then chlorine, bromine, iodine kind of share having a kind of system where they will actually form 4 different common oxyanions. The one in the middle is still the 8, so this would be chlorate. So the most commonly found chlorine oxyanion would have 3 oxygens with a minus charge. If you take one away, just like you would expect, this would be chlorite. Then we just have to come up with a systematic name for naming when we take another O away. Now, we're not trying to predict or say or understand why we don't see that for the first 4. We just don't tend to see things like PO2, 3 minus, just doesn't tend to exist. So we try not to give too many examples of things that just don't exist, even though you could name it by the systematic convention. But we do pick it up for chlorine, the ClO minus. This would be hypo. We use the word hypo out in front and then keep the ite, so hypochlorite. And then if we add an O to the 8, so we go from chlorate, add an O to 4 to go to ClO4, we're going to keep the chlorate ending. We're going to put per out in front. So we call this per chlorate. So we pick up the per, keep the 8, and then we took that second O away, we kept the ite, and then went hypo out in front. So now, we don't necessarily have to go through and write them all for the BrO3 minus, but this would just be bromate. And it can form the ite, the hypoite as well, with the formulas you would expect. It would form the per, so perbromate, BrO4 minus. So we get the same extent of ions like for chlorate, with the 2 minus, the BrO minus, and then even for iodine. So IO3 minus would be iodate, IO2 minus iodite, IO minus hypoiodite, IO4 minus per iodate. So we get the same extent of ions as we would get for chlorine with the same hypoite for the 2 O's removed, etc. Okay, so those are a bunch of anions that we can learn how to name systematically. Let's give you guys a chance just to do, hopefully, a pretty easy problem coming up with the formula of chromium 6 carbonate. So take less than a minute to figure this one out. All right, so let's take a look at this one real quick. And I did look up this phrase since I was alluding to it and should summarize. I'll do that in a minute. But so chromium 6 is chromium 6 plus. So that's what we mean by the 6. Carbonate, we have to know just its charge from either memorizing the silly sentence or just from remembering it's a 2 minus. And so we just know it's a 2 minus, so then we're only going to need 3 of the 2 minuses. So 3 of the 2 minuses gives us a 6 minus. Overall 6 plus from the 1 chromium. Balance out the charges. So our formula here should be Cr1 and then CO3 3 for D. Would be the right balance of charge. Okay, now that silly sentence. Like Nick the camel, so this is nitrate. As we mentioned, the letters for the O's, the vowels for the charge. Camel, this is for carbonate. And so 3 vowels for the charge, or 3 consonants for the count of O's, 2 vowels for the charge. See how silly this is. Clam, supper, so clam was for carbonate, which is weird that you have to remember that that's the second C for chlorine, that this is the ClO3 with the minus. Supper was sulfate, SO4, 2 minus. And crepes is actually one that wasn't on our list yet. I don't think it's even on our summary. It's CrO4, 2 minus for like a chromium salt. Not one I even would worry too much about. But you can see, I think, I think I'm even missing a word somewhere. Oh, Nick was nitrate, never mind. So that's one way to memorize the count of oxygen atoms in the charge. The other way is just to make a couple note cards or to do enough examples. I just have always found that example to be a little silly. Okay, so then we have a system of compounds that tend to exist kind of derived off of some of these anions that we're naming. If you can picture an ion that had a 2 minus or a 3 minus charge, you can probably imagine an H plus ion attaching to that ion. If we start to think about what an acid is, an acid will be something which formally neutralizes the charge with H pluses. So when we finally get to something like H2CO3, we're going to name this in a few moments for being an acid, and there's going to be a special acid nomenclature system. So acids are kind of a special kind of compound where H plus charges are neutralizing the minus charges of the anions. What makes something an acid, we'll talk more about in chapter 4, is when you put it in water, it tends to release H plus ions. And so it's the releasing of these ions into solution, the H plus ion itself, into solution that tends to make something called an acid. But we'll learn how to name acids in a minute. But here, if we're adding H pluses and we kind of don't yet get to the neutral charge, we still have an anion. So we still name something like HCO3 minus like it's an anion. And so then we kind of think, well, what anion is it derived after? So CO3 minus would be derived, of course, off of CO3 2 minus, which is carbonate. So we just call it carbonate. And then to signify that there's a hydrogen attached to the formula, we call it hydrogen carbonate. So an H plus was added, so we reduce the charge now down to minus. So you attach an H plus, we now go down to a minus charge. If we add another H plus, we get to an acid. We'll name that in a moment. So we'll name this thing in a little bit, in a couple slides. If you add an H plus to sulfite, you would call that hydrogen sulfite. So what you're kind of thinking here is, what would the charge be if I remove the H plus? It would be SO3 2 minus. What's the name of that? Sulfite. So I just go hydrogen sulfite for SO3 minus. You can put an H plus onto phosphate. That would obviously be hydrogen phosphate. So ATE ending still. And then you can put a second hydrogen. So if you're looking at phosphate with a 3 minus, you can, let's keep, this is 4. So if you have PO4 3 minus for phosphate, you can imagine adding an H plus, kicks the charge down to 2 minus, and then you can imagine adding a second H plus, kicking this charge down to minus, and still having a negative charge. So we still name an anion like it's an anion. So if you add a second hydrogen to phosphate, that would just be dihydrogen phosphate. And then like any other ion, you can use like something like potassium to balance out the charge and usually get like a normal salt like KCl or K2O. You can get K2 HPO4, where HPO4 is the 2 minus. So you get 2 of the K pluses to balance out the 2 minus charge. Didn't really give myself enough room to write this one, but this would be potassium, and then hydrogen phosphate. So just like K2O wasn't dipotassium oxide, we don't need to call this dipotassium hydrogen phosphate. So just potassium, hydrogen phosphate. And then if you go to H2PO4, you recall that was just a minus. That only takes 1 K plus. So K, H2PO4 would be potassium. Dihydrogen phosphate. And so dihydrogen for the 2 H pluses. So we have some other ions that come up that are just worth memorizing, kind of like a systematic name for a common ion that we'll see. Cn minus is cyanide. Toxic ion, so you don't want to common in like rat poisons and things like that. Hydroxide ion, OH minus, is hydroxide. You guys watched the game on Saturday. It's kind of like reading a chemistry book, kind of put me to sleep. But acetate is CH3COO minus. We mentioned before that you could write this C2H3O2 minus is an alternate way of writing the formula for acetate. So you can either write it CH3COO minus or C2H3O2 minus in a separate way. So 2 ways of writing acetate ion. And then oxygen does have a couple weird ions that are going to come up in some examples. O2 with a 2 minus charge, you might recognize this as the ion behind like H2O2, which you probably know or have seen as hydrogen peroxide. So O2 with the 2 minus is the peroxide ion. And then if you take one of the charges away and go to O2 with a minus, we call this superoxide. So these, with metal ions, they only form a certain alkali and alkaline metals. And if they do form the compound with hydrogen, at least the peroxide does for hydrogen peroxide. You're not going to have hydrogen superoxide as a stable compound, so like HO2, not something you're going to be putting in a bottle and buying at the grocery store, but hydrogen peroxide, something stable enough to put in a bottle and sell. The reason why I'm mentioning here that they only form with certain alkali and alkaline metals is to help us when we start to see things like these 2 examples here. Like if we see NaO2 versus if we see something like TiO2, that when we see sodium O2, that I know sodium's a plus. So because I know sodium's a plus, I know this has to be an O2 with a minus charge. So NaO2 would be the sodium superoxide. And so I know for sure, just based on the charge of sodium, it has to be a plus, that this is sodium superoxide. But then when I see TiO2, Ti is not an alkali or an alkaline metal. Alkali is the first group, alkaline is the second group. We're not getting peroxides and superoxides with our transition metals or any other element. So when I see like aluminum with oxygen, I know it's just oxide ion. When I see Ti with oxygen, I know this has to just be the O2 minus ion. That simple oxide, and I have two of them for a -4. So this has to be a Ti4 plus for titanium 4 oxide. So this compound here would be titanium 4 oxide, and it just could not be the peroxide or superoxide. No. So what this is going to help us with, if we see a compound containing O, if you go, could it be a peroxide or superoxide, it's usually would be, well, it would form in a compound where you know the charge of the metal. So if you had like calcium, like say CaO2, if you're saying, is this oxide, peroxide, or superoxide, I'd say, well, just start with what you know the charge of, which is calcium, which is 2 plus, and so then this would be calcium peroxide. And then if you see a compound where you don't know the charge of the metal, then it has to be oxide. So if you're looking at a compound like Fe, I don't think this exists, but FeO2, again, you're not thinking peroxide or superoxide, you're just thinking, I don't know the charge of iron, so this just has to be an oxide -4, so that's iron 4 oxide, just like the titanium example. Okay, so sometimes when we introduce the nomenclature of peroxides and superoxides, we then get confused on naming other simple oxide compounds. And hopefully we see the distinction. Okay, so here's a relatively quick summary of everything we had just gone over with a lot of examples shown. So like all our halides are minus ions. So fluoride, chloride, bromide, iodide for their systematic names. Oxygen and sulfide are the key ones in the oxygen group. Technically like selenide, Se2 minus could form, but we don't see that in too many examples. But our key examples would be O2 minus for oxide, sulfide, S2 minus. Nitride, phosphide for the nitrogen group with 3 minuses. Carbon tends not to form the 4 minus ion in stable compounds, so we don't talk about carbide or naming carbide, for example. Oxide and peroxide, O2 minus. The symbols in red are ones that are systematically named. The ones that are in black font kind of just have to be memorized. So we just have to know superoxides O2 minus, peroxides O2 2 minus, hydroxides OH minus, acetate is the formula shown, carbonate, nitrate, phosphate, sulfate are what I would memorize with those charges and counts of electrons, and then by default you get carbonate, nitrite, phosphite, sulfite. So just by systematic name, if you know sulfate's SO4 2 minus and you know sulfate's SO3 2 minus. So if we memorize chlorate, bromate, iodate, we get the periodate, the iodite, and hypoiodite. So you get all of these here just by memorizing the one that's in the middle, and then per for adding an O, ite for taking O away, hypoite for taking the second O away. Then we have the hydrogen oxyanions here. So hydrogen carbonate, hydrogen sulfate, hydrogen sulfite, hydrogen phosphate, hydrogen phosphite, dihydrogen phosphate, dihydrogen phosphite are kind of the range of those names. So again, these are all systematic, like you just learn the system and then you learn how to name the ion without really having to put a note card to it and memorizing it specifically. You don't have to specifically memorize H2PO4 minus is dihydrogen phosphate. You're just kind of picking up PO4 3 minus phosphate, 2 hydrogens di, so dihydrogen phosphate. Okay, so let's put a few of these things together. We've done a bunch of examples of these probably already, but let's try to just think of this slide here. Potassium oxide. We'll just think potassium ions K plus, oxides 2 minus, so we got a K2O. So K2O. What about potassium peroxide? We'll just write the charges that you know. O2 2 minus, K plus, so I need 2 of the K pluses to balance out the 2 minus. So it'd be K2O2. I like to contrast the peroxide with that mercury example because it's kind of the same example when you think of that Hg2 with the 2 plus, that this is kind of like the metal example of peroxide, where you would put the 2 chlorines here with the minus to balance out the charge. So Hg2, Cl2 is kind of like K2O2, just where you now have the molecular attachment of 2 cations. like we did with the anions and oxygen. So now what does peroxide look like? Well, it's just two oxygens bonded together somehow with a negative charge on either end. I mean, we'll pick that up later, but that's kind of what peroxide looks like. We get the two charges here, the K plus on one side, the other K plus on the other. So just kind of separating the charges, plus and negatives attracting to each other. Superoxide's the O2 with the minus, so that would just be KO2. So you see for potassium, you could have the range of K2O. For the oxide, that's the most common one that would be the most stable of them, if you will. K2O2 would be another form of an oxygen reacting with potassium for K2O2, and then KO2 for the superoxide. We just did this example, but titanium 4, of course, is Ti4 plus. Oxide's a 2 minus. So, of course, we need 2 of the 2 minuses to balance out the charge, so TiO2. Ti2 is a little weird. If you ever work with paints, people always call this like titanium dioxide. So you might see like titanium dioxide as a common name, or like a name that's often used for this by those like in the paint industry. Titanium's a common dye that makes the white paint. But so you might see things like titanium dioxide, but for this class, we're trying to systematically name this by the systematic rule for an ionic compound, which would be titanium 4 oxide. So I want to give you guys a minute or two to think about CaCN2, Cu2, CO3, and the Zn example. Feel free to work together if you wish. All right, so I don't know if you guys were on track with calcium, and then that's Cn minus is cyanide, so we just have to know Cn with a minus charge is cyanide. So the charges are balancing out 2 plus with the 2 minuses. So calcium cyanide, copper carbonate here. So carbonate we know is a 2 minus, so then I pick up the 2 minus is how I get that the 2 coppers have to have a combined charge of 2 plus. There's 2 of them giving each copper a +1 charge. So a +1 charge copper is copper 1. So sometimes this is a little confusing. Sometimes we want to call this copper 2 carbonate because there's 2 coppers, but that's not what the Roman numeral means. The Roman numeral means what's the charge of copper in the compound. It would be copper with the +1 charge. And then in the zinc example, we would probably look at phosphate first, or phosphite here is a 3 minus. So with the 3 minus, 2 of them gives us a 6 minus. We have to use the main idea here, and the driving force in coming up with these charges is that the overall compound is neutral. So that means I have to have a 6 plus for the zincs to go overall neutral. So 6 plus for 3 zincs gives each zinc a 2 plus charge, which is good because we mentioned zinc with the 2 plus charge is the only common ion of zinc. So zinc 2 plus, we don't have to write the zinc 2 phosphite, we just call it zinc phosphite. So zinc only forms that 2 plus ion. And then ite, because the 3 phosphor 3 oxygens with phosphor is the ite, because 4 is the 8. Okay, now let's get into a couple other types of compounds that we tend to see. Binary molecular compounds are a sort of key group of compounds. A binary is having 2 elements. Molecular is where they're non-metallic elements. And so the way we name these things is generally the element further to the left of the periodic table is often written first. But a lot of times you pick up this by convention. Like when we give you the formula, we usually apply that convention. When we give you the name, we apply the convention too. And so the way we would name most of these compounds is the first element you see is the first element you name. So like in CCl4, we're going to call this carbon for the first element. And then the second element, we use the mono, di, tri, tetra prefixes to indicate the quantity. So we use the Greek prefixes to indicate the number of each element present in the formula. We just don't use mono for the first element. So we don't call it monocarbon tetrachloride. This would just be carbon tetrachloride. It's probably important to also recognize that carbon dioxide and carbon monoxide are systematically named by this convention using the proper rules. So when you see CO, carbon for the first element, then we do use mono for just one of the second elements. So we call this carbon monoxide. And of course CO2, carbon dioxide. And I think there's a slide in a few slides later that has all the Greek prefixes on them. I mean, I think they're just the shapes of a hexagon. You know, so you're thinking penta, hexa, hepta. So for naming these quantities here. So P2O5, diphosphorus. So the first element is just named by the element name, so not like, so just diphosphorus, and then we go to the IDE ending for the second element. So we went chloride for CCl4, so this would be pentaoxide. Now this gets to a weird part where we often just call this pentoxide and get rid of the pentaoxide, but I wouldn't worry too much about that because like I said, we're not usually spelling these things out to know when you're going to call something pentaoxide versus pentoxide. I think both are acceptable names. But pentoxide is what you usually see more commonly for P2O5, N2O, dinitrogen monoxide. That does have a more common name. Does anybody know N2O? I think that's nitrous oxide is what that's more commonly referred to as. But we systematically name it as being dinitrogen monoxide. CrO3, trick question, is this a binary molecular compound? This is a ionic compound. So this is named by the systematic ionic compound names. I just want us to make sure that we start to see NaCl, KCl, all those compounds we were just naming as being ionic compounds, not molecular compounds. So this would not be chromium trioxide. This would just be the usual name, chromium 6. Not 4, chromium 6 oxide, using the ionic compound systematic nomenclature system. So we just have to, so when we're looking at a compound that contains 2 elements, if they're both non-metallic elements, so hydrogen and then left side elements in the periodic table, then we name it for being one of these systematic molecular binary compounds. Let's talk about acids. So acids in some cases look like binary compounds, but acids are, when we think of these compounds, usually in water. So usually we're naming like HCl in water, not as like a gaseous molecule or, you know. So our acid nomenclature, we're going to pick this up. This will tie into chapter 4 a little later too on the difference between like a normal compound and something that behaves as an acid in solution. But something in solution will disassociate to the ions. And that's what really makes something become an acid in water. But our acid nomenclature would kind of begin with recognizing like chloride ion for HCl. And when we have the simple atomic ion, it takes the systematic name hydroic acid. So this would be hydrochloric acid. So hydro and then chlor, the root name of the acid, so hydrochloric acid. HBr would be hydrobromic acid for bromide ion. And then we have a systematic name for ates and ites to their acid form. So let's do the ates first. So the ates to acid form just takes the name ic acid. So an ate-derived acid. So if you derive an acid off an oxyanion with an ate ending, so this just kind of means for HClO3, think about ClO3, what its name is, that's chlorate. So the acid of a chlorate would be chloric acid. So hopefully we see here HCl, hydrochloric acid, and then chloric acid, ClO3, HClO3. If we look at HClO4, ClO4 is perchlorate, so this would be perchloric acid. There's two acids that if I came across in a laboratory I would never touch, never use, because they'd probably blow me up or melt my skin away. One would be perchloric acid. It'd be very easy to have a reaction turn explosive if you don't know what you're doing, so be very careful if you ever work in a laboratory. I wouldn't use perchloric acid without very special training. And does anybody know the other one that would eat your skin away? What acid would you probably not want to work with the most? Is HF, believe it or not. Hydrofluoric acid, incredibly nasty. If you actually work with dilute, you usually think, well, if I have a dilute acid, probably not so bad. You get the dilute acid on your skin, you don't realize it's on your skin, it's eating your flesh away. And you don't even realize it. You don't have much time to get treatment either. So do not work with HF. Do not work with perchloric acid. Sometimes we name things, we start thinking, oh, we know the name of it, we can work with it. So be careful. I mean, strong acids and bases are hazardous to work with too, so don't think I'm saying HCl is without hazard. You have to be very careful working with strong acids in the laboratory as well. But they're maybe not as hazardous as some of the things like perchloric acid and HF. Hydrofluoric acid, of course, would be the same. So HClO, so if we recognize the ite ending of the anion in its acid form, we need to know a name that's different for like ClO2 from ClO3. So the ending for the ites are us acid. So HClO2 would be chlorous acid. So chlorite to chlorous acid. And then hypochlorite to HClO would be hypochlorous acid. So a good nomenclature system could look at all these acids here and name them differently, and they do. So we have to have a different name for HCl, from HClO to HClO2 to HClO3 to HClO4. So if you notice, all of those acids have a systematic name that's different from each other. A couple more systems that are pretty straightforward to kind of, because you've seen a lot of these examples, like methane is the saturated hydrocarbon of carbon. So by saturated, we mean that carbon can form 4 bonds. So if all 4 of those bonds are with hydrogen, that's methane. If you have 2 carbons and you saturate those carbons with hydrogens, that ends up being 6 hydrogens because there's 6 spots left to form 4 bonds on each carbon. So that would be ethane. So this would be C2H6. And then if you take 3 carbons and connect them together, that's propane. So how many hydrogens? Well, 3, 2 more, and then 3 more. So we might write this CH3, CH2, CH3. Either way that we're writing it, that this is propane. So propane is a saturated hydrocarbon with 3 carbons. Butane is a saturated hydrocarbon with 4. I won't attach all 4, but I'll just write CH3, CH2, 2 CH3. That would be butane. And then penta through deca would be the case of having 5 to 10 carbons, and we just saturate with the proper number of hydrogens. So for decane, CH3, CH2, 8 of them, CH3. So deca would be 10. So 2, 9, so 2 of the CH3s in the end, plus the 8 in the middle, gives us a 10 total count of carbon atoms. And then the count of hydrogens would just be 8 times 2 in the middle, CH3s on the end to give us the 4 sets of bonds for each of those. I'll probably give this as a reminder next time, but if we replace a single hydrogen with the hydroxyl group, that just becomes the alcohol that we call the methanol, ethanol, propanol. Okay, so we'll give a little bit of, we'll pick up from naming these alcohols, give a reminder on hydrocarbons. There's a few extra slides on naming